Usually, when we picture the front line of cybersecurity, we think of this, hyper-modern laser battle, right?
Always the latest 0 days clashing with AI defenses.
Exactly. But if you actually look at the threat landscape right now, specifically the dispatches from just the last 48 hours, it's honestly more like an archaeological dig.
Right. It really are.
And the ancient artifacts we're uncovering are, they're certainly springing to life and actively compromising infrastructure today. So welcome to today's deep dive. We are synthesizing 3 urgent stories from May 17th and 18th, 2026. And the overarching theme here is, we're calling it the ghosts of code.
It is the absolute definition of dealing with the ghosts of code. I mean, we are fighting vulnerabilities that were written when Windows Vista was still a thing.
It's wild. So whether you manage massive servers or, write code or just use the standard Windows PC, these 3 stories directly impact your security right now. We've got a server bug from 2008. We have leaked open source malware wreaking havoc, and a patched Windows vulnerability from 2020 that just resurrected itself.
A literal zombie bug.
Yeah. So let's start right at the foundation, the infrastructure layer. We are looking at a critical heap buffer overflow in NGINX.
Right. Specifically in NGINX Plus and NGINX Open, the vulnerability actually resides in the HTTP rewrite module,
Okay.
which is the part responsible for modifying URIs based on regular expressions.
And the timeline here is what immediately caught my attention when I was reading the Depth First security report. This memory corruption bug was introduced into the NGINX codebase in 2008.
18 years ago.
Yeah, but Vulncheck is reporting active exploitation attempts against their honeypots, like right now.
And the mechanics of this are, well, they're fascinating when you look at how that rewrite module handles memory allocation. If an attacker sends a maliciously crafted HTTP request, specifically manipulating the headers or the URI to trigger a really deeply complex regex evaluation, the buffer that's allocated on the heap for that rewritten URI, it fails to correctly account for the final size.
Got it.
So it just, overflows into the adjacent memory chunks.
Okay, let's unpack this because I want to push back a little on the actual severity in a modern environment.
Sure.
If you look at the exploitation requirements to achieve remote code execution here, they are just incredibly steep.
Oh, extremely.
Right. Security researcher Kevin Beaumont noted that beyond needing a very specific non-default configuration, address space layout randomization ASLR has to be entirely disabled on the target machine.
Which is, incredibly rare on any production system today.
Exactly. It's like having a heavily armored vault, but the attacker needs you to, explicitly leave the vault door and latch to get the gold.
Yeah.
If ASLR is enabled, the memory layout is randomized. So trying to execute an RCE payload is like trying to parallel park a massive truck blindfolded.
While the parking spots keep randomly shuffling around you.
Right. You're going to hit unallocated memory, and the process is just going to crash. So if reliable RCE is essentially a dice roll on a modern server, why are the AMA Linux maintainers officially calling this an urgent patching priority? Threat actors don't typically waste their automation bandwidth on impossible exploits.
Well, what's fascinating here is that you just hit on the exact reason it is urgent. You mentioned that hitting unallocated memory crashes the process, right?
Yeah.
That is the actual objective here.
Yeah.
RCE isn't the only goal an attacker might have. In a highly distributed infrastructure environment, a really reliable denial of service is often, just as damaging.
Okay. So they are weaponizing the failure of the RCE.
Precisely. NGINX worker processes are designed to handle thousands of concurrent connections, right? So if an attacker sends these malformed HTTP requests, even without the precision you'd need for RCE, they reliably crash the worker process. The master process will try to spawn a new worker, but a really simple, lightweight Python script sending just a dozen crafted requests a second.
It'll just continuously crash them faster than they can boot up.
Exactly. Every single valid connection just drops. It is an incredibly cheap, highly asymmetrical DOS attack that takes a massive web server completely offline.
Wow. Okay, well, that makes the honeypot activity make a lot more sense.
Okay.
But to really understand how attackers are, scaling these infrastructure attacks right now, we need to look at the other major discovery Volncheck published alongside this regarding OpenDCIM.
Right. The open source data center infrastructure management software.
Yeah.
And this is a prime target because it inherently holds the keys to the kingdom. I mean, it maps out physical servers, networking gear, power distribution.
All the critical stuff. And Volncheck found a whole cluster of critical flaws here, but two of them really stand out because of how elegantly they just chain together.
Yeah, the authentication bypass.
Right. So the first is an authorization bypass that relies on Docker configurations.
Yeah.
If you have a reverse proxy setup where the remote user header isn't strictly sanitized before being passed to the backend container, an attacker can simply inject remote user admin into their HTTP request.
And the backend just blindly trusts the header.
Exactly.
Yeah.
And suddenly they have full administrative access without even touching a login screen.
It's a classic trust boundary violation. The application assumes the proxy handled the authentication, and the proxy assumes the application is, validating the headers.
Yeah, everybody thinks the other guy did the security check.
Right.
And once they bypass authentication, they move to the second flaw, which is an operating system command injection in a component called reportNetworkMap.php. The system takes a parameter named dot and just passes it directly to a shell execution function without stripping out any shell metacharacters.
Meaning the attacker just appends a semicolon and then drops a reverse shell payload straight into the bash terminal.
Yep. Volncheck noted an attacker can achieve a full reverse shell in just 5 HTTP requests.
5. That's incredibly fast.
But the mechanism of discovery is the real story here, I think. Caitlin Condon from Volncheck reported that the activity they are tracking against OpenDCIM originates from a single Chinese IP address. But it isn't a human operator manually probing these endpoints.
Right, they are using AI.
Yeah, they're using a customized implementation of an AI vulnerability discovery tool called VulnHunt.
And this fundamentally changes the economics of attacking infrastructure. Volnhunt isn't just a dumb fuzzer, it's an autonomous agent.
Right.
It can actually analyze the target source code, recognize that remote user trust boundary failure we just talked about, dynamically construct the spoofed headers, navigate to the vulnerable PHP script, and then inject the precise bash payload required for that specific OS environment.
So it is literally reasoning through the exploit chain in milliseconds.
Exactly, and that is why a 2008 NGINX bug and a 5-request OpenDCIM chain are so dangerous right now. In the past, finding and chaining these legacy vulnerabilities required a human to, spend hours doing reconnaissance and custom payload development.
Right, it took effort.
Yeah. Now, threat actors just point Volnhunter at a subnet, and the AI handles the discovery, the logic, and the execution completely autonomously.
Yeah. So the practical takeaway here for anyone managing these environments, obviously, apply the NGINX patches from F5 immediately.
Yeah.
But structurally, you have to audit your trust boundaries.
Yes.
Verify that your Docker reverse proxies are aggressively stripping out client-provided remote user headers, because you cannot rely on obscurity anymore. An autonomous AI agent has all the time in the world to find the one header you forgot to sanitize.
And, if AI is making it that effortless to automate attacks on hardened servers, it perfectly explains the shift we are seeing in human threat actors right now.
Oh, for sure.
They are looking for a higher return on investment.
Which transitions us perfectly to the supply chain layer. Because if attacking the machine is being outsourced to AI, the human attackers they're shifting to tricking the developers instead.
Mm-hmm.
We have 4 new, highly malicious packages discovered on the NPM registry, and they were all uploaded by a single user.
Right, and the NPM registry is the absolute backbone of the JavaScript ecosystem. When an attacker poisons this well, they aren't just compromising one server, they are infecting the build pipelines of potentially thousands of applications.
Yeah. So the packages were published under slightly varied names. We've got Chalk Template, Deadcode 09284814 Axios Util, Axios Utils, and Color Style Util.
Such classic typo-squatting names.
Exactly. Let's look at the mechanics of Axios Utils first. Instead of just being a generic info stealer, this package actually drops a Golang binary called Phantom Bot. It's a highly capable distributed denial-of-service botnet.
And using Golang is a very deliberate choice for malware in a supply chain attack. Yeah, because it allows the attacker to cross-compile the payload for Windows, Linux, or Mac OS architectures just seamlessly.
Ah, right. And it establishes deep persistence, too. Like on Windows, it quietly copies itself into the startup folder and generates scheduled tasks. So once it's embedded, it just beacons out and waits to receive instructions to initiate HTTP, TCP, or UDP floods against secondary targets. The developer's workstation essentially just becomes a zombie node
Yeah.
in a global botnet infrastructure
But the payload in that other one, the Chalk template package, is arguably much more sophisticated.
because of its self-replicating nature, right?
Exactly.
Yeah, it drops a direct clone of the Shai-Hulud worm.
hmm
For context, this is a piece of malware that a group called Team PCP open-sourced and leaked literally just last week.
Yeah, fresh off the press.
When a developer accidentally installs Chalk Temple, the worm immediately scans their local environment for .shash and .oz directories to harvest cloud credentials.
Which is bad enough.
Bad enough. But then it uses the developer's own local Git configuration to push a brand new public repository to the victim's GitHub account.
Wow.
It weaponizes the victim's infrastructure to host the next generation of the worm, and then it tags the repo with the description. A mini SHA-1 Hulud has appeared.
It's highly performative, you know, almost theatrical.
Yeah. But here's where it gets really interesting. The distribution method. Axioy utils instead of Axios. Chalk template instead of Chalk template. This relies entirely on typo squatting. It's like someone putting a fake ATM right next to the real one and just hoping you're walking too fast to notice the logo is misspelled.
Right. It isn't a complex dependency confusion attack where they're like exploiting private registry routing.
No.
They are just injecting a malicious dependency into the public registry and relying on a developer being too tired or typing too fast to notice the transposed letters.
Or relying on developers blindly copying and pasting installation commands from AI chat assistants.
Oh, absolutely.
But look at the use of a leaked open source worm and the performative GitHub descriptions. I have to ask, is this just a script kiddie having fun with open source malware? Or is there a larger structural trend happening here?
Well, if we connect this to the bigger picture, OX security provided some crucial context that points to a major structural shift.
Okay.
The cloning of the Shai-Hulud worm was actually directly inspired by a supply chain attack competition.
Wait, a competition?
Yeah, hosted on the hacker site Breach forums shortly after Team PCP leaked the code.
They are running literal competitions for supply chain compromises. That's insane.
They are gamifying the destruction of developer environments, and this really highlights a terrifying reality about the barrier to entry right now. I mean, the original author of the Shai-Hulud worm spent considerable time engineering the evasion techniques, the credential harvesting logic, all the self-replication protocols.
Right, the hard work.
But the actor behind these NPM packages, they didn't have to write any of that. They simply copy-pasted the leaked code, routed the command and control traffic through a .ler.life localhost tunnel to hide their actual infrastructure, and just uploaded it to NPM.
So they essentially outsourced the malware development to the open source community.
Precisely. And OX security characterizes this incident not as an isolated event, but as phase one of an upcoming wave. When a single low-skill actor can effortlessly deploy cross-platform DDoS botnets and self-replicating worms just by relying on developer fatigue, the threat landscape becomes incredibly volatile.
Yeah, so the direct actions for you, the listener, need to be aggressive here. First, audit your package.json files and log files immediately for those specific package names. And if you suspect an accidental installation, you cannot just uninstall the package and call it a day.
No, absolutely not.
The Shai-Hulud worm has already exfiltrated your AWS tokens and SSH keys. You have to rotate all cloud and crypto secrets system-wide, and you specifically need to search your organization's GitHub footprint for that bizarre string, a mini SHA-1 Hulud has appeared.
Just to see if your developers are unwittingly hosting the next hop of the worm.
Exactly. And block all network traffic to .ler.life domains at the firewall level to sever those C2 tunnels.
And you mentioned earlier that the perimeter is shifting. I mean, if a type-squatted package slips past a developer, the perimeter is breached. The attacker is inside the house.
Right, which transitions us perfectly to the endpoint layer, because we have a vulnerability that essentially guarantees that once they are inside the house, they own it completely.
Yeah, this one is rough.
We are looking at a zero-day vulnerability in the Windows kernel dubbed Mini Plasma, and it was discovered by a researcher known as Chaotic Eclipse.
And the mechanism of this vulnerability is deeply, deeply embedded in the Windows architecture. It exploits clds.lt.easys, which is the Cloud Files mini filter driver.
Right, so for context, this is the driver responsible for handling file placeholders. When you use something like OneDrive, the actual file lives in the cloud, but you see a placeholder icon on your desktop.
Right.
When you double-click it, cldflt.sys intercepts the I/O request, pauses the execution, fetches the file from the cloud, and hands it back to the user process.
Exactly. And the vulnerability exists within a specific routine called HSML's block placeholder access. It's a classic timing vulnerability, specifically a race condition.
Okay, so how does that play out? An attacker initiates a request to access a placeholder file, and the filter driver begins processing the permissions, right?
Right. But before the kernel actually finishes validating the security token, the attacker aggressively manipulates the memory state.
Or swaps the file handle.
Yes. Because of the tiny window between the time the driver checks the permission and the time it actually uses the object, it mistakenly evaluates the context of a different, highly privileged process.
Ah.
The result is the attacker's payload gets executed with system privileges.
And system is the absolute highest level of control on a Windows machine. It operates above even the standard administrator account. It allows the attacker to load custom kernel drivers, blindly terminate endpoint detection and response tools, and just completely manipulate the registry.
Total control.
So what does this all mean? I mean, the technical execution of a race condition isn't even the most shocking part of this dispatch to me. It's the timeline.
Oh, the timeline is wild.
This exact vulnerability in that routine was originally discovered by Google Project Zero researcher James Forshaw back in September of 2020. And Microsoft supposedly patched it in December of 2020.
Supposedly.
Right, because the original proof of concept code that Google published in 2020 still works perfectly today, completely unmodified, to spawn a system shell. Chaotic Eclipse proved it, and Will Dorman confirmed it works reliably on Windows 11 systems running the absolute latest May 2026 updates. It's like hiring a contractor to fix a leak in your roof. They bill you for it, and 5 years later it rains and you realize the hole was literally never patched.
Yeah.
How does a major tech company silently roll back a critical kernel patch, leaving a 5-year-old privilege escalation bug wide open?
This raises an important question about the unimaginable fragility of legacy code bases. I mean, the NT kernel is monolithic and it's just deeply intertwined. Fixing a core filter driver like cldflt.sys without breaking the entire Windows file system is like trying to replace a load-bearing pillar in a skyscraper while the building is completely full of people.
Right.
You might reinforce the pillar in 2020, but let's say a massive architectural update to OneDrive in 2023 requires altering how file handles are processed.
Okay, I see where this is going.
The engineers resolving the merge conflicts unknowingly overwrite the security reinforcement to prioritize system stability, and suddenly you've reintroduced the exact same structural weakness.
And because the regression was never tracked, the ghost was just sitting in the machine waiting for someone to run the old Google Project Zero script.
And we know this specific component is under immense pressure from attackers. I mean, Microsoft had to patch an entirely different privileged escalation flaw in this exact same filter driver just a few months ago, in December of 2025, that was being actively exploited in the wild.
Wow. Okay, so let me play devil's advocate here for a second.
Sure.
Dorman noted that because this relies on a tight race condition, you only get a tiny millisecond window in memory. If your timing is off, you don't get system privileges. You just blue screen the target machine. Furthermore, this is a local privilege escalation. They already have to be running code on my machine to trigger the race condition. If I've already lost the perimeter to an open source worm like Shai Hulud, why should I care if they escalate to system? Isn't it already game over?
It is absolutely not game over, and this is why defense in depth is the only viable strategy here. Think about the NPM packages we just analyzed.
Yeah.
If a developer runs npm install axoy utils, that malware executes in user space. It runs with the permissions of that specific developer. It can steal local files and drop scheduled tasks, sure, but it is highly visible.
Right.
Modern EDR solutions running in the kernel will spot the anomalous network traffic or the unauthorized registry modifications and terminate the process.
So it's contained in a sandbox, relatively speaking.
Exactly. But if that user space malware triggers the mini plasma race condition and jumps to system, the attacker crosses the boundary into the kernel. They can now cleanly uninstall your EDR, wipe the event logs, and install bootkits that actually survive system restarts.
Oof.
They transform a noisy, easily detectable user space infection into invisible, permanent infrastructure. That is why local privilege escalation matters. It is the bridge between a temporary breach and total network compromise.
And because there's no patch available for Miniplasma today, your only defense is ensuring they never get the chance to run that initial user space code. You have to aggressively secure the perimeter because the interior foundation is currently cracked.
Which ties everything we've discussed today together pretty perfectly.
It really does. So to quickly summarize our journey, we started at the perimeter, looking at a 2008 NGINX vulnerability being hunted at scale. We moved to the supply chain, where human attackers are gamifying the deployment of leaked worms via typo-squatting to breach developer workstations. And we ended deep inside the operating system, where a resurrected 2020 kernel bug provides the perfect bridge to total system control once that workstation is compromised.
And, while we've been analyzing these as distinct tactical layers, there's a much broader strategic shift happening just beneath the surface of these reports.
Yeah.
We noted that attackers are using the Hunter AI to autonomously compromise servers, right? Well, at the exact same time, in the remediation steps for the NPM supply chain attack, OX Security specifically had to advise organizations to scrub malicious configurations out of their AI coding agents, like Claude Code.
Oh, wow.
So I want to leave you with this thought. Are we rapidly approaching an inflection point where the cybersecurity battleground isn't human defenders patching against human attackers? We might be entering an era where offensive AI tools are dueling directly with our AI developer assistants, executing race conditions and complex exploit chains at a speed and scale that we simply cannot even monitor.
It's an entirely new paradigm, and the ghosts of legacy code are just the ammunition. We'll be tracking exactly how this AI-driven threat landscape evolves in our next deep dive. Thanks for joining us today, and stay secure.